Section 18.5 Quantum Mechanical Rotation in 3 dimensions. 3-dimensional one-particle rigid rotor assumes the radius of the rotation is a constant, r0. The Schrodinger equation is this. On the left-hand side, you are looking at H psi. On the right-hand side, it's E psi. H is a Hamiltonian. H is the sum of the kinetic energy operator and the potential energy operator. And now we are looking at 3-dimensional rotation. Therefore, we have 3 variables x, y, and z. But among these 3 variables, only 2 are independent variables. The third one depends on the other 2, because x squared plus y squared plus z squared is r0 squared. And now, if the particle is moving on the sphere with this r0 radius, the potential energy is 0. If the particle leaves this sphere, the potential energy is infinity. So that means the particle can only rotate on this sphere with a radius of r0. Now let's look at this r, theta, phi polar coordinates. We have x, y, z Cartesian coordinates in this picture. R is the distance between the particle and the center. Theta is the angle between the r vector and the z-axis. And this dashed line is the projection of r on the xy plane. The angle between this projection and x is phi. So we can convert xyz to r theta phi. And also we can convert r theta phi back to xyz. So x is r0 times sine theta cosine phi. Y is r0 times sine theta sine phi. Z is r0 cosine theta. All right? So this dashed line, the projection of r on the xy plane is r0 sine theta. And this r0 sine theta times cosine phi will give us x. It times sine phi will give us y. By the way, this theta corresponds to the latitude of Earth. Phi corresponds to the longitude. The conversion from the polar coordinates to xyz is here. R is the square root of x squared plus y squared plus z squared. And tangent theta is, again, the projection of r on the xy plane, this one, over z. That's tangent theta. All right? Tangent phi is simply y over x. Now we can convert this Schrodinger equation in the x, y, z Cartesian coordinates to r theta phi coordinates. We need to use the chain rule in multivariable calculus. So delta psi over delta x, this is how psi changes with x, is equal to the sum of the 3 products. This is because when x changes, r changes. When x changes, theta changes. When x changes, phi changes. When r changes, psi changes. When theta changes, psi changes. When phi changes, psi changes. In this case, because r is a constant r0, for the rigid rotor, then we can delete the first term. R never changes. We still have two terms here for delta psi over delta x. We have these two terms for delta psi over delta y. We have only one term for delta psi over delta z, because z does not depend on phi. Now let's evaluate delta psi over delta z. Well, because this one is the easiest. Now we'll just do some mathematical trick here. This is delta theta over delta z. I changed this to delta tangent theta over delta z times delta theta over delta tangent theta. All right? So this is actually delta theta over delta tangent theta. All right? And then we know this one is cosine theta squared. This one is here. So anyway, if you do the derivation carefully, you'll get the same result as I got. The second derivative is simply the first derivative of the first derivative. So now we look at this first derivative. We realize the first derivative operator is negative sine theta over R naught delta over delta theta. So we apply this operator twice to psi. First derivative, second derivative. Again, do this carefully, you get this expression. This is the second derivative of psi with respect to z. Similarly, you can convert this two in the polar coordinates. It's just much more complicated and much more tedious. Now let's just assume we had done this already. And then we got the Schrodinger equation in the polar coordinates. We have theta here, we have phi here, and this I is simply m r naught squared. I is the moment of inertia. And this is for one particle system. If we have a two particle system, I is mu times r naught squared. And 1 over mu is 1 over m1 plus 1 over m2. R naught is the distance between the two masses. And again, we are assuming the distance between these two masses is a constant. We can solve this Schrodinger equation and get some solutions. There are an infinite number of solutions. I'm showing you the first few. The first one is just a constant. The second one is a constant times cosine theta. The third one is sine theta times e to the plus minus I phi. I want to talk about this actually three functions. This one is simply z over r, right? Because z is r times cosine theta. So this is z over r, or z over r naught. This one. Okay, actually there are two Eigen Functions here. The quantum numbers are, well, we have a L quantum number, that's 1. We have another quantum number, m sub L, which is plus minus 1. In this case, whenever you see a imaginary number in a function, you know this function does not have a real physical meaning. Well, that's normal. A quantum mechanical wave function often does not have any physical meaning. But we can do a linear combination of these two functions. Remember, e to the power of plus I phi and e to the power of negative I phi can be used to make sine phi and cosine phi. In this case, sine theta times sine phi is going to be y. Sine theta times cosine phi is going to be x. So you're looking at the linear combinations of x over r and y over r here. And this is z over r. And now if you pay attention to these two symbols, L and M sub L, you may have related this to the quantum numbers of the electrons in an atom. And they have the same meaning, indeed. For electron in an atom, you have N, the principal quantum number, you have L, the angular momentum quantum number, M sub L is the Z component of L, and then you have M sub S, the spin, right? So you learn this for quantum numbers in general chemistry. If you get a more rigorous general chemistry book, there is another quantum number S. M sub L to L is similar to M sub S to S. So anyway, let's get back to this. We are actually talking about Z over R here, and this is X over R and Y over R. So you are looking at something very similar to the PZ orbital, and over here, linear combinations of px and py orbitals. And now I'm going to show you 5 more solutions. This is one solution. There are 2 solutions here. Look at this plus minus I phi, and over here plus minus 2 I phi. You are looking at 5 wave functions similar to dz squared, dxz, and dyz, dxy, and dx squared minus y squared. So really, in this wave function, you are looking at 3 times z squared over r squared minus 1. Over here, you are looking at the linear combination of xz and yz over r squared. Over here, you are looking at just xy, the linear combination of xy and x squared minus y squared over r squared. So again, these solutions to the Schrodinger equation for the 3-dimensional rotation correspond to the s orbital, p orbitals, and d orbitals. I'm now showing you the picture of those solutions. This is the first solution, a constant. It does not depend on theta or phi, therefore it's spherical. The 3 p-type wave functions, 5 similar to d orbitals, and of course, this 7 are similar to the f orbitals. And again, we need 2 quantum numbers. One is L, one is M sub L. L is 0, 1, 2, 3. M sub L can be from negative L to positive L. So let's get back to this. L is 0, M sub L is 0. L is 0, M sub L is 0 or plus minus 1. L is 2. M sub L can be 0, plus minus 1, or plus minus 2. All right. Now we can get the 3-dimensional rotational energy. The expression is this. It's L times L plus 1 times h bar squared over 2I. So if you know the value of I, and you know the quantum number L, you can calculate the rotational energy. All right? You do not need to know the value of I to calculate the angular momentum, because the rotational energy is the angular momentum squared over 2I. So really, this numerator is angular momentum squared. Therefore, the magnitude of the angular momentum is this. The square root of L times L plus 1 times h bar. So by looking at this h bar, you know the unit of angular momentum is joule per hertz, or joule times second. There's one thing really interesting and surprising. The rotational energy of s electrons is exactly 0. no matter you have 1s, 2s, 3s, 4s electron, L is 0. If L is 0, then the angular momentum is 0. The rotational energy is 0. Again, this is surprising, but this is also the result of solving the Schrodinger equation exactly. Now let's look at the z direction. If we focus on the z direction, if we look at the rotation about the z-axis, we can compute the rotational energy about the z-axis fairly easily. It's just m sub l squared times h bar squared over 2I. The angular momentum in the z direction is just m sub l times h bar. Alright? So this is the magnitude of the angular momentum, the three-dimensional angular momentum. And this is the z component of the three-dimensional angular momentum. Well, by looking at this, you should realize that when L is 1, m sub L can be -1, 0, and 1. So you should be able to draw three vectors with the same magnitude, which is the square root of 1 times 2, then times h bar, square root of 2 times h bar. That's the magnitude of the three-dimensional angular momentum. Its z component can be h bar, 0, and negative h bar. Now let's look at one specific example. I'm giving you this eigenfunction, which is just cosine theta times a constant. This is just the normalization factor. This part is usually trivial. We'll just apply the Hamiltonian to this eigenfunction and see if we can get a constant multiplied by this function. Now the Hamiltonian is here. Alright, this is the Hamiltonian in the polar coordinates. We apply this Hamiltonian to the eigenfunction. If you apply this to this, you get 0 because theta does not depend on phi. And then you just need to evaluate the first derivative of cosine theta. It's negative sine theta times sine theta. You get sine theta squared, and then we take the first derivative of sine theta squared, and then divided by sine theta. So anyway, it's a little tedious, but it's doable. In the end, you will be able to get the original wave function. So this is this wave function multiplied by a constant. That constant is the rotational energy. It's just h bar squared over I. We can also use this equation to calculate the rotational energy by plugging in L equals 1. Well, we got the same expression, h bar squared over I, h bar squared over I. All right? And again, the rotational energy is the magnitude of L squared over 2I, and then we have the magnitude to be square root of 2 times h bar. Right? And we can also apply this z component of angular momentum to this wave function. And this is the z component. All right? We apply this to this. It looks fairly complicated, but cosine theta is simply z over r naught. And now you can see z does not depend on x. Z does not depend on y. This result is 0. That means the z component of this wave function is simply 0. All right? So what does that mean? That means if you look at this wave function, that means, well, its rotation energy is this. We have the angular momentum. It's square root of 2 times h bar. However, its z component is 0. So this vector is on the xy plane. All right? It's on the xy plane. Well, again, you took general chemistry, and you know the angular quantum number is L. And this m sub L is the z component of L. There's another name for m sub L. It's magnetic quantum number, because you can pass a bunch of electrons through a magnetic field and separate them based on this m sub L as well. This is again the z component of the angular momentum. It's equal to m sub L times h bar. Now, we were talking about electrons. What if we work on molecules? If we work on the rotation, the three-dimensional rotation of linear molecules, we will write out similar equation, similar Schrodinger equation. And we'll solve that equation. We'll get similar Eigen Functions and a similar expression for the rotational energy and angular momentum. There's only one difference. By convention, for molecules, we do not use quantum number L. We use quantum number J. That's the only difference here. The three-dimensional rotational energy is J times J plus 1 times h bar squared over 2I. I is mu r squared, and mu is the reduced mass of the diatomic molecule. All right? And then if you have a linear molecule, well, you can still calculate this I. You find the center of the mass first, and then you look at the distance between every single atom and the center. You can still find this I. About the rotation in the z direction. All right, so this means the rotation is about the z-axis. The rotation energy in the z direction is m sub j squared times h bar squared over 2I. Again, I is the moment of inertia. M sub j is a quantum number. M sub j can be from negative j to positive j. So M sub j can adopt 2j plus 1 possible values. All right? So you can count, from negative j to positive j, there are 2j plus 1 possible values. The z component of the angular momentum is simply m sub j times h bar.